Enrique, you're around here somewhere. I think I see your. There you
Yeah,
are.
hi.
All right, man. You want to share your screen and get cracking?
Yep. So, hi, I'm Enrique. I'm the co-founder and CTO at Pipeshift. Today I'm going to be talking about the hidden complexities of open source CI. So, this will mainly cover a lot of things that if you're someone who's worked on with open source models, any libraries, or any modules, you would have come across some of these. For those who have been working with OpenAI, have plans to, let's switch over to open source and see what is there to offer. These tips might come handy, like some gotchas about what problems you could come across. So, uh, in the hidden complexities, we mainly have like two separate sides. So, one is mainly around the libraries and modules that are part of this open source ecosystem. So, the inference engines, the tokenizers, how the chat template works, how to get multi GP working. And then on the other end, we have all the infrastructure related kind of problems. So how do I set up my Kubernetes clusters, get the orchestration, scheduling working, handle auto scaling challenges, load balancing. So in today's talk, I'm going to be covering most of the things on the libraries and modules, since like the event is agent R, it just felt better to stick to like more core AI stuff instead of going like infra heavy. Uh, So before I get dive deeper into most of the challenges, I'll just give a simple explanation about what chat templates are, because I've noticed this to be a thing. Like, this is a very basic concept, but surprisingly, a lot of people I've spoken to seem to not be aware that this is a thing, even though they have used it. So basically, the concept of a chat template is that when we talk to any of these open source models, whether while creating fine tuning data sets or making inference requests, we'll usually have this messages array of sorts. We would have like a system prompt, user prompt, these kinds of things. And a lot of people's default assumption is this is how the model basically sees the input. But actually, what happens is we have this concept of a chat template. And basically, what we do is we pass this to a chat templating kind of like a function, and basically, it outputs this kind of string. So you can see this has like a bunch of special tokens. You can see the system and user prompt. Uh, so this is what the models finally see, and not this top JSON. This array doesn't make any sense to them. We just throw it in the model. The model will most probably output something, but it's not going to be at the quality that you expect it to be giving an output of. This example string that I have here is of the Llama 3.1 chat template. Uh, as you can see, it ends with the assistant prompt over here, which, even though it's not there over here, that is mainly because LLMs, they kind of do completion of sorts. So when you like give it this assistant piece, it knows like, okay, I'm supposed to continue writing the LLM response over here. Uh, Now this chat templates are again dependent on various models, so you have to be careful while applying them. Of course, Hugging Face makes it kind of easy. It is just they just have a chat template function where it goes to the files of the model and it just applies it. This is one of the conversations I had with one of my customers that somehow happened to know that okay, chat templates are a thing, and they were like worried if they are supposed to pass the template or how it's supposed to work. And then we were like, okay, we just handle things, and they were happy. So now, covering this, I want to explain what happens if you're someone who has already, you have a fine-tuned model, and like a new model comes, how do you go about changing things, what to look out for. So I'm taking this example around vision models. So this particular example is of the Qwen 2 VL. Uh, so as you can see here, the way Qwen 2 VL works is, uh, in the array that we are passing over here, the type is image URL. This is also standard with the OpenAI's API. So if you're using OpenAI's API for any vision calls, you would also pass the key as image URL. So basically, if you're creating a data set for fine tuning Qwen 2 VL, this is also the kind of format that you would use. Now, 1 month after Qwen 2 VL came, 1 month, approximately a month around that time, we also got Llama 3.2, the 11B vision. Now, what happened with this particular model is, if you notice here in the messages array, uh, instead of using the image underscore URL key, uh, llama has the image key. So now let's say, assume you created a data set that had image underscore URL or your inference stack and various logging pipelines everywhere tracking for image URL. This kind of key suddenly breaks your entire flow. So these are like, this is one of the things that you have to be careful about. So a lot of people just assume like, okay, if I'm upgrading a model, all I'll do is I'll just change the model name, I'll just change my import statements from transformers and everything will work. But that might not necessarily be the case. There would be some minor changes here and there that you need to be careful for. Next, I would like to talk about multi-GPU fine-tuning, and specifically for faster training times. Now, why I'm focusing more on faster training times is because there are multiple strategies when we talk about multi-GPU. So that is mainly on the parallelism front. So parallelism is they are basically strategies on how, uh, given a model, how do I like spread it across a bunch of GPUs. So one very popular one in this is called tensor parallelism. So tensor parallelism is mainly used for larger models because you can't fit a lot of them on a single GPU. So what basically happens is you shard the model weights across the multiple GPUs. So you can see in this example you have 3 GPUs. In practice we can't shard across 3. There have to be like multiples of 2. So it's either 2, 4, 8, that kind of config. Uh, So yeah, so this is mainly for for either larger models, or let's say a smaller model you want higher performance, so you take like a 7 or 8B and you would shard it across 2 or 4 GPUs to get like the increased performance and throughput. Then we also have pipeline parallelism. This is again for larger models, but it doesn't really give you like a performance boost. I would say this is mainly used in situations where your bandwidth between your GPUs is limited. And then again, in the later part, I'll also talk about different GPU bandwidths and things that you have to look out for over there. But yeah, that is, at least that is where I've usually seen this comes applied. Uh, right now, I'll be talking mainly about data parallelism. So in data parallelism, what we basically do is we basically replicate the same model across all the GPUs, like the exact same copy, and then we basically break our data set into like smaller mini batches of sorts, and then they compute across all the GPUs in parallel. So one basic strategy that we have is called data parallel, and then we also have distributed data parallel I'll talk about next. So in data parallel, basically what happens is the first GPU basically reads the entire data and it creates mini batches that it sends out to each of the GPUs. And then the model is also replicated like from the first GPU to all of them. You execute a forward pass, you collect the outputs from all the GPUs, send it to GPU to the first GPU where the loss is computed. uh, Again you take the loss from that GPU, send it out to distribute it to all the rest of the GPUs, run a back propagation, and then again collect an average. So this is one strategy to do it. uh, Another strategy is, this is the preferred way to do it if it has to be done, is distributed data parallel. So in here what we do is the main process, so on the first GPU we basically create like a master process of sorts. And now what happens is, instead of this main GPU like creating these mini batches and like sending the loss to all of them, to all the subsequent GPUs, uh, each of the GPUs by themselves consume the mini batches, or like the main process of it gives it some guidelines. So yeah, you consume the mini batch, you do the uh, your forward backward pass over there itself, and then you just do a reduce to get an average of the losses and then run your gradients. Now, of course, the main difference why I said that distributed data parallel is preferred is, in data parallel, since as I mentioned earlier, that the first GPU like reading it and then it's sending it out again, collecting it. So the first GPU kind of has a lot more load compared to the rest of the GPUs. So this basically creates underutilization in the rest. Like apart from the main GPU that is running, almost all the other GPUs will be underutilized. So DDP does a significantly better job over there. Now, some things that we need to be careful while implementing DDP is, first of all, you have to deal with this concept of partial state. Uh, I won't go over a lot in this. Basically, just initialize it to a function. The main thing what you need to be careful is, since you're replicating your model and your computation across GPUs, let's say you have logging statements or these kind of print statements everywhere, you basically need to check that, okay, you only log it once on the master process or the main process, as its main process, the technical term. Uh, if you don't do this, what will basically happen is every the model gets loaded into, let's say, 8 GPUs, so you would have like 8 log lines printed saying model loaded into memory. So every time you hit a print, like, you just get 8 lines, which is like just messy for your logs and stuff. So this is a minor thing. Maybe you're fine with 8 lines being logged, which is not a big deal. The bigger thing that you need to be careful with is that, while basically saving the model, you again need to make sure that the save, like saving, I'm talking like post training, the save is happening only after checking that is being saved from the main process that is on the first GPU. Because if you don't do this, at least when we had first implemented DDP and we had like somehow skipped this out because it wasn't obvious in the docs, we ended up in a situation where all the uh, basically model weights got merged in a single one. So basically, let's say if I'm running my if I'm doing LoRa based fine tuning on 8 GPUs, and each adapter, like my final adapter is supposed to be like 500 MB. Basically, what happens is all this 8 GPUs somehow push the model together, and the final adapter was like 500 MB into it. So it became like a 4 GB adapter for some reason. Maybe it was a bug, or I don't know, but just one small thing to be careful about. Now, next, I'll talk about switching between inference engines. Here we have like this example of how do you make calls to VLLM. This is like pretty straightforward. VLLM is also pretty easy to install and run. You just have like one installation command where you pass the model name, it downloads it, spins it up, pretty simple to run. You have a basic call request that follows OpenAI format. uh, yeah, this is pretty standard stuff that most people know about. Now, let's say you are running this, and you decided like you want to switch over to something like Triton TensorRT, because you notice that maybe it's giving better performance for certain models, better latency, better throughput. Again, it depends on your use case and on your configuration. Again, Triton and TensorRT is like, there are tons of configurations that you can mess around with to get better performance, or even worse if you mess it up. Now, over here, you would first one notice is the endpoint looks very different. So for the OpenAI standard endpoint, we usually have this chat completions part at the end, but over here we have this ensemble generate. Now over here, if I had to pass something like the system and user prompt, you would think like, okay, I'll just add it as a string over here, and then the model would work as is. But the tricky part over here for TensorRT specifically that you be careful is that TensorRT doesn't auto apply the chat template for you. So what I spoke about earlier. So if you give it the input like this is exactly how to pass it to your model, and then your model is not going to be able to comprehend the input correctly, and you're going to get like a very messy output. So basically, what you need to do is you need to manually run like the chat template function, get this kind of string, and pass that to the model. So this is like one mistake that people tend to make, like if you have not used it before, like because it just seems kind of obvious, like okay, it's written text input, I'll just dump it in and it's going to work. It doesn't work that way. Next, I'll talk about hardware selection. So, in hardware selection, things tend to get a bit tricky because, so let's say you are running some experiments with some model. You started on with AWS, you spun up an 8NG instance because it was like not very expensive, like one of the low cost GPUs, you can easily spin it up and run. So, let's say you got a model walking, you're trying to run some inference experiments with VLLM, TensorRT, whatever. You notice that okay, maybe now it is too slow, you want like a slightly more powerful GPU, so you think okay, let's spin up an A100 and see. Now the issue is on AWS, the only A100s you can get are an entire node of A100, so you'll have to spin up like 8x A100, which it costs like I think 40-50K a month, which is like crazy expensive. So you think like okay, like, I'll just skip AWS. I'll see who else has a cheap A100. Turns out Azure, you can spin up single A100s on Azure for pretty cheap. Uh, so you go ahead with Azure, you spin up a VM there, figure out whatever network configurations, get everything up and running over there. Then you suddenly feel like, okay, like A100 is good, it's a bit expensive. And then you also learn about FP8 quantization, since in default, usually most people run, like the models we're running on FP16 by default, if you don't set anything. So you want to try out, let's say, FP8 for, because, sorry, because when you do FP8, basically you don't lose that much accuracy while still getting pretty decent performance, since your bandwidth utilization goes down significantly. Turns out on Azure, the only GPU with H100 is with FP8 support is H100. So in the process of trying to find a cheap FP8 GPU, you end up with a L4 on GCP. Now you realize that, okay, you want a maybe slightly more powerful card, since L4 is pretty low powered. So again, you end up in this loop where again back on AWS for something more powerful, FP8. So one thing with GPU selection is it you have to be like ready to like play around with different clouds, because each one has some pros and cons. AWS has A100s, H100s. They are like, you have to spin up the whole nodes, others are pretty expensive. Azure has a pretty limited set of GPUs. Uh, GCP has a bunch of other stuff which again AWS doesn't have. So just some things to keep in mind when you're like testing out things and exploring options of which hardware you can play around with. Now another thing that people don't realize with A100 specifically, I mean, it's also kind of things with other GPUs, H100s and L4s also have this concept, but more over in A100. So in A100 we have like 4 different configurations. We have like a 40 GB card. So we have 2 VRAM configs, first of all, 40 GB and 80 GB. And then we have 2 connectors that are supported, that is PCI and SXM. So what you need to be careful is that a lot of times people will just see like, okay, I'm getting an A100 here on this provider, A100 on this provider, and just compare price and spin it up. But then your performance can be like really very different. So if you just compare the difference between a PC and SXM connector, you can see that if you're running like FP16 compute, you can get like double the performance on SXM versus like 312 teraflops over here, which is like a huge difference over here. And then even like if you compare between uh, the amount of VRAM that you're getting, a lot of people think like, okay, I just need the bigger VRAM if I have a big model, so I'll stick with a smaller one. But you in fact have a pretty significant uh, bandwidth difference as well. So here you can see there's like a 30% improvement in bandwidth, and bandwidth is really important when you're talking about inference, because usually in LLM inference, that is the first thing that chokes out. Like we choke out on bandwidth before we choke out on compute. Uh, of course, again, there's things around the interconnect performance and things like that. So yeah, every A100 is not the same. Uh, Now coming more towards the end, this is something that is a bit more chaotic. There's no simple fix for this. This is just an example that we once came across while we were building things with the models, that I just called it tokenizer chaos. So for when we were working on the Mistral 7B, this is I think the V.2, we ended up with this situation where when we were doing a streaming output, this is the kind of output that we got. And basically the problem that happened over here while debugging, we realized is that while doing the streaming, we were getting a small, like the way Streamworks, you get the small chunks out. And basically what happens is on the chunks, when you run your tokenizer to convert it from the, basically the token to text translation, it was for some reason stripping out the spaces. So as you can see, like you can see the words are correctly written, but there are no spaces between things. Now there's no fixed solution for this, and this problem happens between varying models. We have also seen this happen with, I think, one of the Falcon models in the past, as well as either it was Llama 2 or Llama 3 also had this. similar kind of issue. Again, it is a variation. It isn't exactly this, but then it leads to this kind of problem. So the fix that we came up with is basically we had to like accumulate the tokens and like run the tokenizer and the whole thing, and then we had to like apply a slicing logic to like just send the new generated token out, like post the token to string conversion. So yeah, these are just some things that we have come across while building Pipeshift. These are some of the things that you might have seen, some of the things that you might face. And small, so basically, what we are building at Pipeshift is a modular orchestration platform for open source AI components, so that you can easily run like vector DBs, embeddings, LLMs across any cloud or on-prem. So if you're someone who's building with open source LLMs for your company or team, and you see some of these challenges, not just this, but even on the infrastructure side of managing Kubernetes clusters, orchestration, scheduling, then like yeah, happy to talk and help you out.
Excellent. So the thing that I wanted to ask you is on the performance for like Triton and VLLM. You said there's a bunch of ways that you can get better performance there.
Yeah.
Can you elaborate on any that you liked?
Uh, yeah. So the thing with Triton is Triton TensorT is that you can think of it. It's more like a, I would say like a library or compiler or sorts, you can call it. So basically, what you would need to do is, unlike VLLM where you just do, you just install the package and run it. For TensorRT, you basically have to build these engines, and while building them, you need to specify flags. Like you can mention like, okay, I want flash attention enabled, and then I want page attention on or off, and then I'll set like, okay, this is going to be my input size, it's going to be my output size, it's going to be my batch size. So based on that, what basically happens is we end up with uh, basically TensorRT behind the scenes compiles is kernels depending on your configuration. So I would say if you have a good idea about, I think a pretty simple thing would be if you just have a good idea about what your input and outputs are going to be and what batch size you expect. I think that itself could give you a significant performance boost instead of like just throwing in a huge number. And then beyond that is just sticking to some things like flash attention, some other recommended kernels also there that TensorRT has in their docs.
Excellent.